Another sort of different type of development is the theory of solitons as it emerged from Martin Kruskal and his collaborators' work, and you got involved pretty early on.
That is correct.
You knew about the numerical work even before it was published, I guess.
That is right. I knew Kruskal personally, and I learned his famous discovery with Zabasky of the interaction of solitary waves. You may remember that when von Neumann became interested in computing, he realized it was not only of great importance for designing nuclear weapons, but many other big engineering problems. But being von Neumann, he realized computing will have an equal impact on theoretical mathematics, because von Neumann said, if a problem comes up, very often we don't know where to start. We don't know what the phenomena are, and we need some information that's usually provided by physical experiments. A computing experience can replace the physical experience. And that's what happened exactly with Kruskal and Zabasky. They performed numerical experiments with soliton and discovered the exact separation. So that was very remarkable, and I started thinking about it. And my thinking went to something like this. Given an arbitrary initial function, as time progresses, there issue from it solitary waves. And the speed of these solitary waves, I realized, were invariants in time. There were infinitely many of them, well, presumably infinitely many. So then I started thinking, how could you prove the existence of infinitely many conserved quantities at one stroke? Well, one way to do it is to have these conserved quantities as the eigenvalues of an infinite dimensional operator. So then that led me to what is called lax pairs.
Did you have any idea how important this would be as you were doing it?
I knew that it was a general idea, not just for KDV. I was a little bit surprised at how many applications it would have.
And some years later, you came back to KDV to study the zero dispersion limit.
That is right.
And would you say a little bit about what was that question and why you thought it was important?
Well, in mathematics in general, when certain parameters appear which have physical values, the limiting behavior is important. For instance, for Schrödinger equation, the limit from quantum mechanics to classical as h tends to 0 is important. In fluid dynamics, where you have Reynolds number, which is the reciprocal of a small number, the limit as Reynolds number tends to infinity is important. So I thought likewise this might be important, or at least interesting, and it was.